This is problem set 5. We took the A and we used reduced row echelon form. We built the x4 all the way to x1 to x5. We set up the null, which is S times a vector, T times a vector, or S times a matrix C, T times a matrix C. Found the subspace. The number of those are 2. That's the nullity. Now what you're going to do is transform it. Now we're going to transform this. Transpose it, I should say, transpose A, T, okay? So when I transpose it, it's going to be 1, 3, I don't like that color. This is how we find the rank. 1, 3, 1, negative 2, 1, 2, 6, 4, negative 8, 3, and then you have negative 1, negative 3, 1, negative 2, 5. Now what I'd like you to do is to do reduced row echelon form for that. Give that a try. Reduced row echelon for the transposed, A of transposed. So reduced row echelon form for the transposed one. I want to see if your calculators are going to do it. This is what I got. Did anybody else get? You got that? Yay! Good. Did you get this, Henry? Oh. What did you do? You add 2 more columns of zeros? Okay. Super. You didn't have to do that here, did you? Did you have to do that here? No, just for this one. Okay, good. That's interesting. So now, what this is if you take this, this, and this, you're going to see that these correlate to these. These are called the row space. So you're going to take the row space of these. The first one, 1, 0, 0, 0, 0, it's going to be 1, 3, 1, negative 2, 1. And because you got 3 of these, you're going to have 3 of these. 2, 6, 4, negative 8, 3, and negative 1, negative 3, no comma. Negative 1, negative 3, 1, negative 2, 5. And this is called the row space. And how many of those are there? How many of those are there? 3. Because you got 3 of these. The rank is 3. And what's the nullity plus the rank of A? 2 plus 3 equal 5. And to prove this theorem is correct, this nullity plus rank should equal to the number of columns in the original A. And how many columns are there in A? 5 columns in A. So you did it. You proved it. Well, I would just do these, add them up to get 5, and just say, oh, in A, there's 5 columns. Is that all right? Let's go to 2. I'm going to get this done. 2 is so fast, don't blink. Okay? Oh, you blinked. It's too late. You missed it. No. You're going to get a linear combination of T 4, 6. So we have T 1, 0 plus T 1, 2, and you want to get T 1, 6. I love the gradiated colors, but not when I'm doing this. Okay, T16, 46. So how many of these can I get to get close to T46? How many? Yeah, so if you do 3 of these, do you see how I get 2 times 3 is 6, 3 times 1 is 3? Okay, so I need 3 of these. It'd be easier if this were 0, 1, but they're not doing it that way this time. They're doing this. So just 3 of these will give me 6 here and 3 here, and then how many of these will I need? 1. Do you see that? And then, what's T of 1, 0 equivalent to? It is equivalent to 1, 3, and that's times 1. And then this one, T of 1, 2, what's that equivalent to? T of 1, 2. Negative 1, negative 3. And there's 3 of those. So you're going to have 1, 3 plus negative 3, negative 9. That's going to be negative 2, negative 6. That's the answer to that one. Seems too easy, doesn't it? Does it make sense? Did I do any fast sleight of hand? Aiden, you okay? Yeah. Okay. Last one for today. Consider a T4 transformation, linear transformation to R2. And we're going to find kernel, range, nullity, and rank. I would love it if we could get this done before you leave today. Would just make my day. So we start off in terms of x and y. I'm going to write this in terms of x and y. We have, for the kernel, x plus y minus z, y plus w minus x should be equal to 0, 0. That's what we're trying to solve for the kernel. The kernel is the values that will give us the solution ax equals 0. Okay, so what I'm seeing here is that x plus y minus z equals 0. Y plus w minus x equals 0. And the ones that are common here are x and y's, right? So let's solve for z. What's z equal to? X plus y. Here, what's w equal to? X minus y. Love it. So the kernel, this is part A, the kernel of T is going to be x. Let's see, we've got x, y. Oh, I did it this way. I like this. X times something plus y times something. So for x, it's just going to be 1x. For y, it's going to be no y's. And then it's going to be w has 1x, and z has 1x in it. For y, there's no x and a y. In regular y, there's 1y. There's in w, there's a negative 1y, and in z, there's a 1y. Okay, so the kernel for this, if you want to, you could also say, this is the way I like it, it's x, y, x minus y, x plus y. So do you see how I got this? 1, 0, 1, 1, and this one's 0, 1, negative 1, 1. Does that make sense now? That's the kernel of T. And I think that the range of that thing Oh, okay, so I've got this linear combination. Oh, I was so close. Linear combination is going to be 1, 0, 1, 1, and 0, 1, negative 1, 1. And that's going to be a nullity of what? How many of those are there? 2. And then for the range, watch the video. I'm going to keep going here. So BW is equal to T of B that they had. And then this is equal to X plus Y minus Z because it's 2 dimensions. Y plus W minus X. And then you just say, oh, it's X times 1, 0 plus Y times 1, 0 plus minus Z times 1. See you guys. Plus Y times 0, 1 plus W times 0, 1 minus X times 0, 1. Put all the 1 zeros together and you're going to get X plus Y minus Z times the 1 zeros plus Y plus W minus X times the 0 ones. And that will give you a linear combination, our range of T of 1, 0, 0, 1. And it has a, what do they call that? A rank? Rank of 2.